What specific problem does the Step1X-Edit method aim to solve in the context of image editing with natural language instructions?
The Step1X-Edit method aims to address the performance gap between open-source and closed-source image editing systems, particularly in the context of following nuanced natural language instructions while maintaining high image fidelity. It focuses on improving the alignment between input images and editing instructions, especially for subtle or compositional edits that existing models struggle with. By leveraging a large-scale, high-quality dataset and a unified architecture that combines a multimedia large language model, MLLM, with a diffusion model, Step1X-Edit enhances semantic reasoning and visual manipulation capabilities. This approach ensures comprehensive coverage of diverse editing tasks, enabling more accurate and context-aware image edits. Ultimately, Step1X-Edit seeks to provide a scalable, interactive, and user-grounded solution for image editing that meets real-world user needs.
How does the Step1X-Edit algorithm work? Illustrate it step by step, including how it integrates the MLLM and the DIT-style diffusion architecture.
The Step1X-Edit algorithm operates through a structured three-component framework: a multimedia large language model, MLLM, a connector module, and a diffusion in transformer, DIT architecture. First, the input editing instruction and the reference image are processed together by the MLLM, such as QuenVL, which captures the semantic relationships between the instruction and the visual content. Next, the relevant token embeddings are isolated by discarding those associated with a system prefix, allowing the model to focus on the specific editing requirements. These refined embeddings are then passed to a lightweight connector module, which restructures them into a compact textual feature representation that replaces the initial text embedding in the downstream DIT network. Finally, the DIT utilizes this enhanced semantic comprehension to generate the output image, effectively combining structured language guidance with high-fidelity image synthesis for accurate and context-aware editing operations.
Can you come up with a simple yet illustrative example on the inner workings of Step1X-Edit, detailing each step with a hypothetical image and editing instruction?
Certainly. Let's consider a hypothetical example where the input image is a landscape photo featuring a bright blue sky and a green field, and the editing instruction is, change the sky to a sunset with orange and pink hues. 1. Input processing. The landscape image and the editing instruction are fed into the multimedia large language model, MLLM, such as QuenVL. The model processes these inputs in a single forward pass, capturing the semantic relationship between the instruction and the visual content. 2. Token filtering. The model selectively discards token embeddings associated with a system prefix, retaining only those that align with the editing instruction, which in this case emphasizes the transformation of the sky. 3. Feature refinement. The retained embeddings are then passed through a lightweight connector module, which restructures them into a compact textual feature representation. This refined feature replaces the initial text embedding in the downstream diffusion in transformer, DIT network. 4. Image generation. The DIT network, now equipped with enhanced semantic comprehension from the MLLM, generates a latent representation of the target image. This representation incorporates the desired sunset colors, while maintaining the integrity of the original landscape. 5. Output creation. Finally, the model synthesizes the output image, resulting in a visually coherent landscape where the sky has been transformed into a beautiful sunset, effectively following the user's instruction while preserving the overall aesthetic quality of the scene. This example illustrates how Step1X-Edit integrates multimodal reasoning with diffusion-based synthesis to achieve high-fidelity, semantically aligned image edits.
What are the theoretical or practical benefits of using Step1X-Edit compared to existing open-source and closed-source image editing systems?
Theoretical and practical benefits of using Step1X-Edit include its ability to significantly outperform existing open-source models like OmniGen and ACE++, while approaching the performance of leading closed-source systems such as GPT-4o and Gemini2 Flash. Step1X-Edit integrates a multimedia large language model, MLLM, with a DIT-style diffusion architecture, allowing for enhanced semantic reasoning and context-aware editing, which addresses limitations in instruction alignment and image fidelity seen in prior models. The model is trained on a large-scale, high-quality dataset of over 1 million image instruction pairs, ensuring comprehensive coverage of real-world editing scenarios. Additionally, the introduction of the GEdit-Bench benchmark allows for authentic evaluation against practical user editing needs, further validating Step1X-Edit's effectiveness. Overall, Step1X-Edit not only bridges the performance gap between open-source and closed-source systems, but also provides a user-grounded approach to image editing that enhances both accuracy and quality.
How is the performance of Step1X-Edit validated or tested using the GEdit-Bench benchmark in terms of metrics and experimental design?
The performance of Step1X-Edit is validated using the GEdit-Bench benchmark, which consists of over 1,000 real-world user editing instances categorized into 11 distinct groups. The evaluation employs 3 metrics: semantic consistency (SQ), which measures adherence to editing instructions, perceptual quality (PQ), assessing the naturalness and artifact presence in images, and an overall score derived from these evaluations. The benchmark includes both English and Chinese instructions, allowing for comprehensive testing across different languages. During the evaluation, results are reported for 2 subsets: the intersection subset, where all models successfully return results, and the full set, which includes all testing samples. Step1X-Edit demonstrates superior performance across 11 evaluation axes, outperforming open-source models and achieving comparable results to closed models like Gemini2 Flash and GPT-4o, particularly excelling in style change and color alteration tasks.
What limitations or drawbacks does the Step1X-Edit method have, particularly in relation to scalability, complexity, or generalizability?
The Step1X-Edit method, while innovative, does face limitations in scalability and generalizability, although it integrates a multimedia large language model (MLLM) with a diffusion architecture to enhance semantic understanding and editing fidelity. The reliance on a sophisticated data pipeline and extensive training data may hinder its scalability to diverse editing tasks beyond the 11 predefined categories. Additionally, the complexity of the model, which involves multiple components such as the connector module and token refiner, could pose challenges in terms of deployment and real-time editing applications. Furthermore, while the model shows strong performance against existing open-source and closed-source systems, it may still struggle with incremental editing and fine-grained region correspondence, which are essential for more nuanced user instructions. Lastly, the model's performance may vary significantly based on the quality and diversity of the training data, potentially limiting its generalizability across different editing scenarios.